Hi, we meet again. So we are going to continue from part 3 into part 4, still in processor structure and function. We are still in 14.4, continuing with instruction pipelining. In part 3, we mentioned some of the situations that can result in less than optimal pipeline performance, like branching and also interrupt. In this part 4, we will examine this issue in a more systematic way. A pipeline hazard occurs when the pipeline or some portion of the pipeline must stall because conditions do not permit continued execution. Such a pipeline stall is also referred to as pipeline bubble. There are 3 types of hazard: resource hazard, data hazard, and control hazard. In the next slides, we'll show you in more detail each of these hazards. The first type of hazard is resource hazard. It occurs when 2 or more instructions that are already in the pipeline need the same resource. The result is that the instruction must be executed in serial rather than parallel for a portion of the pipeline. A resource hazard is sometimes referred to as structural hazard. Let us consider a simple example of a resource hazard. Assume a simplified 5-stage pipeline in which each stage takes 1 clock cycle. The figure in this slide shows the ideal case in which a new instruction enters the pipeline each clock cycle. Now assume that the main memory has a single port and that all instruction fetches and data reads and also write must be performed one at a time. Further, we're going to ignore the catch. So let's go back first. Students need to remember that operand can be in memory or register. Yeah. So here fetch operand and also write operand. If it's in the register, no problem. Yeah. But if it is in main memory, yeah, that's where the problem happens. Because in this case, an operand read to or write from memory cannot be performed in parallel with an instruction fetch because instruction fetch is also using the memory. In this example, yeah, we are going to assume that the source operand for F1, yeah, so here the fetch operand for instruction I1 is in memory. Not register, not catch. So at time 3, at clock cycle 3, you see that I1 is using memory for fetch operand, and also I3 at time 3 is also wanting to use the memory because it is supposed to fetch the instruction from the memory. So we have conflict here. I1 and I3 is trying to access the memory. One to fetch operand, another one is to fetch instruction. So what is the solution? Here. I3 should allow I1, yeah, to use the memory first to fetch the operand. So therefore, I3 has to be idle because it cannot enter memory. Memory is being used by I1. So the fetch instruction stage of the pipeline must idle for 1 cycle for I3 before beginning the instruction fetch for instruction I3. So this figure also assumes that all other operand are in register. So no other conflict except between I1 and I3 during trying to use the memory, one for fetch operand and one for fetch instruction. So that is an example of a resource hazard. After resource hazard, the second hazard is data hazard. It occurs when there is a conflict in the access of an operand location. The way I can explain it is this way. Yeah, we have two instructions in a program which are to be executed in sequence, and both access in a particular memory or register operand. Yeah, so two different instructions trying to access the same register operand or the same particular memory. If the two instructions are executed in strict sequence, meaning you finish all instruction 1 first, yeah, then only you go to the second instruction, no problem occurs. However, if the instructions are executed in a pipeline, then it is possible for the operand value to be updated in such a way as to produce a different result that would occur with strict sequential execution. Yeah, meaning before instruction 1 has finished updating, yeah, instruction 2 use the same operand but the old value. That means the result of instruction 2 is wrong. So let's look at an example here. Yeah, this is an x86 machine instruction sequence. So we have first add EAX, EBX, and then sub ECX, EAX. Before looking at the table, we can see that, yeah, we might have a problem for EAX register. Yeah? Because in pipeline, you are doing the stages in separate stages. So before EAX can be updated, yeah, with the add instruction, sub has already fetching EAX, and that might be the old value of EAX instead of the current value after instruction 1. Let's look at this figure, yeah, that shows the pipeline behavior. So we know fetch instruction, so it fetch add EAX, EBX, and then it will decode and see whether you need indirect addressing, okay, whatever. So then you fetch the operand. So now the operand is in register, no problem. You go to get it from EBX, yeah, and then execute instruction. So it will be doing the adding. And lastly, when do we update the latest value of register EAX? It is until the end of stage 5, which is write operand. This is where, yeah, here we update EAX value. Okay, so far so good. Now let's look at the second instruction. Okay, so it will start at time 2. So fetch instruction, no problem. You get it from the memory, sub ECX, EAX. Then you decode the instruction, see? And then you should go to, you're supposed to start fetch operand. You're supposed to go get the content of EAX and also ECX. But, yeah, because you're doing it in parallel, right? So if you go and get EAX, it will not be the latest EAX value because it only happens after clock 5. So in here, if you do it, you will get the old EAX value. So this is where data hazard happen. So if you're using pipeline, what we need to do is we need to idle the stage for instruction 2, for sub instruction. So to maintain the correct operation, the pipeline must stall for 2 clock cycles, for 2 clock cycles. It can only fetch operand, yeah, after cycle 5, yeah, after the 5. So here, right, it can only fetch here, alright. Therefore, in the absence of special hardware and specific avoidance algorithm, you can see that, yeah, such this data hazard actually results in inefficient pipeline usage because you have to introduce 2 idle stages. If I can give you a real example of numbers, EBX is 2, EAX is 5, yeah, and then ECX is 2. All right. So if it's strict, what you get here? What do you get here? Okay, I'm going to put the answer here. You should get 7, yeah. Then here, so 7 minus 2 should be 5, the result. However, yeah, because you're doing pipelining, so instead of 7, at this junction, right, you are using the old value of EAX, which is 5, and you get the wrong answer, which is 3. So wrong. Yeah, you must use the correct one. So in order for you to use the correct 7 and get the correct answer 5, you need to idle this. Good? Yes. Now the third hazard. A control hazard, also known as a branch hazard, occurs when the pipeline makes the wrong decision on a branch prediction and therefore brings instruction into the pipeline that must subsequently be discarded. I will explain in detail after this slide, yeah, how pipeline is actually wasting a few instructions because of branching. There are a few approaches to dealing with control hazard, but we are going to focus on delayed branch. Not branch, branching, delayed branch. So I'm showing you this figure. Yeah, in this example, we have an extra stage, which is CO. Yeah, CO is calculate operand. So fetch instruction, decode instruction, calculate operand, fetch operand, execute instruction, and write operand. Okay, let's go. Instruction 1 and 2 are normal instructions. However, we're going to assume that instruction 3 has conditional branch. Yeah, jump or jump not 0. Okay. And it will jump to instruction 5. Skip instruction 4. However, because we are in a pipeline, there's no way we would know that there's a branch, meaning there's no way we can understand, we can know that we are going to skip instruction 4. Yeah? So that means, yeah, pipelining is happening. So instruction 4 comes in here, 5 comes in here, even 6 times up, yeah, 7, instruction 7, fetch instruction happening there. So when do we know that branching is happening? We know branching is happening at when we execute. Yeah, until the instruction 3 is executed, there is no way we know which instruction. Yeah, there's no way we know that we should go to instruction 5 instead of instruction 4. So before we arrive at EI, yeah, pipeline happens normally. Yeah, all fetch instruction comes in, DI comes in, CO comes in. So the pipeline just simply loads the next instruction in sequence, yeah, and proceeds as usual. After instruction 3 has executed the instruction and found out that it's actually going to branching to instruction 5, so all other, yeah, here it stops. Yeah, nothing here. So why? Yeah, so pipeline will stop taking all these other stages because it knows that it has to branch to another instruction. And then all unuseful instruction, yeah, the one that comes in before we know that there's branching, will be cleared. So after we know branching happens here, yeah, that means we're going to instruction 5, but we're not going to this instruction 5 because this one has been cleared. Yeah, it has to restart. You cannot go to the fetch here. No. So you will go to fetch, will go here. So instruction 5 instead, yeah, have some delay, and then you start here, fetch instruction. Okay. So I5 only starts at unit 8, time 8. Okay, so there's no instruction here. All right, so it's what we call a branch penalty. Yeah, so the performance is not good for pipeline in this case because there's a branching, because we cannot anticipate the branch. So because we didn't anticipate, we just put in all the earlier instruction, yeah, 5, 6, 7, without knowing there's a branch and without knowing that we didn't actually need them. So yeah, the performance penalty incurred. 4 clock cycles wasted because of instruction 4, 5, 6, and 7. Let us show you a second example of control hazard. Okay, so we have these instructions in yellow box here. So we have instruction 1, instruction 2, instruction 3, and our branching happens in instruction 4, and it will jump to instruction 11, ignoring 5, 6, 7 until 10. So instruction 1, 2, 3 happens normally, yeah, normal in pipeline. Then instruction 4 gets into the pipeline, and after execution, all right, here the pipeline realized that it needs to do branching. But before we arrive, yeah, just before 7, before we arrive at time 7, I5 comes in with F1 and DI. I6 also comes in. Yeah, as soon as time 6 finish here, as soon as this finish, nothing comes in. Yeah, there's nothing here. Nothing comes in. And also here, nothing. It stops. All right. Because pipeline realized that, yeah, it tak perlu. It doesn't need I5, I6 until I10, because from I4 it needs to jump to I11. I11 will comes in after, as soon as we have realized that I4 is branching, yeah, after EI here. So it will start at cycle time 7. It is possible to improve pipeline performance by automatically rearranging instruction within a program. So how do we do that? So we're gonna rearrange so that there is no wasted instruction. Yeah. So the branching happens and then straight away goes to the target. So what we need to do is we need to know how many instructions should I4 jump. So we need to know the number of segments. So in this case, it is 4 only. So 4 minus 1, you get 3. So you need to jump 3 instructions. So your I4 originally is here. So you jump 1, you jump 2, you jump 3. Yeah. So your I4 will be at the start. So if you see, yeah, so we're going to start with I4. So meanwhile, yeah, I2 comes in, no problem. I3 comes in, no problem. And then at here, I4 and pipeline realized that it found a branching instruction, so it needs to go to I11, right? Because jump lossy. So after SR, it needs to go jump 11, and there is no problem because there's no wasted instruction. Because I2, I3, I4 are all instruction before the original jump. So as soon as finish SR, I11 can automatically goes into the pipeline. So no wasted instruction happens. So this solution is a good solution for control hazard. Also, instead of I11 started at time 7, you can see we saved instruction cycle and started earlier at time 5. We closed down subsection 14.4 by looking at instructive example of an instruction pipeline of Intel 8486. The 8486 implements a 5-stage pipeline: fetch, decode stage 1, decode stage 2, execute, and lastly write back. With the use of 2 decode stages, the pipeline can sustain a throughput of close to 1 instruction per clock cycle. However, complex instructions and conditional branches might slow down this rate. Moving on to subsection 14.5, the x86 organization has evolved dramatically over the years. In this subsection, we're going to look briefly at some of the details of the most recent processor organizations. Table 14.2 showed the organization of the register, which includes the common registers that you're familiar with: general, flags, instruction pointer, status, and so on. This is the E-flags register, extended flags, which indicates the condition of the processor and helps to control its operation. It includes the 6 condition codes that you are very familiar with. Sign, 0, auxiliary, parity, and carry. In addition, there are also bits in the register that may be referred to as control bits, like trap flag, interrupt flag, and so on. It also has MMX registers. So do you remember from chapter 12? MMX is single instruction, multiple data instruction set designed by Intel, used for multimedia extension. It has 8 MMX registers, and it is also, you can map it with a floating point. Intel 8486 also has interrupt processing within its processor as a facility provided to support the operating system. It allows the application program to be suspended in order that a variety of interrupt conditions can be serviced and later resumed. There are 2 classes, interrupts and exceptions. You just have to read and get to know. After we have looked at the Intel processor, the last subsection, 14.6, is the ARM processor. So we're going to look at some of the key elements of the ARM architecture and organization. ARM is primarily a RISC system, reduced instruction set, with the following attributes. Please have a read. The ARM processor organization varies substantially from one implementation to the next, particularly when based on different versions of the ARM architecture. However, it is useful for the discussion in this section to present a simplified generic ARM organization, which is illustrated in this figure in this slide. if we are comparing with the instruction design in 14.3, yeah, there's familiarity. So let's see. We have PC. So in ARM, we call it incrementer. And then it will go from PC, from incrementer, it will go to memory address register, right, MAR. And from MAR, it will go to memory. From memory, it will go into memory buffer register. And from memory buffer register, MBR, we go to IR, instruction register. Yeah, so ARM also follow that standard processor organization. This is the end of chapter 14. You have looked at processor organization, register organization, and then quite a lot in instruction cycle and instruction pipelining. And briefly, we look at x86 processor family and ARM processor. So after this, we are gonna go to control unit in chapter 20. See you in the next lecture video. Bye.